Okay, so in a previous video we talked about changes of state and we calculated the heat of fusion. That's the energy that it requires for an amount of substance to melt or to freeze. We're going to talk now about a couple more changes of state and we'll do some more calculations. All right, so we're going to talk about sublimation and deposition. These are weird. We don't talk about sublimation and deposition very often, right? So sublimation is when you get a gas. Nope, it's the opposite. And sublimation is when you get a solid, it goes to a gas, right? Very unusual. You're probably not used to seeing this. And a gas going to a solid, that's deposition, right? Well, it takes a certain amount of heat to get the solid to go to a gas. I guess the example is, you know, where we live, where we're used to things like water, right? Well, in water at 1 atmosphere where we live doesn't go from a solid to a gas. It goes to a liquid first. But carbon dioxide does. And you may have seen a block of dry ice before. At 1 atmosphere, if you put a block of dry ice on your bench, it's not going to turn to liquid. It's just going to go straight from a solid to a gas, right? Because that's the way carbon dioxide does at 1 atmosphere. So we can describe more about that later. But for now, this is a little bit of an unusual change of state. Sublimation, solid to a gas. Sublimation happens when the particles of the surface change directly to a gas, which I said already. There's no change in temperature. Okay? No change in temperature for sublimation. Deposition is just the opposite. And there's the example of dry ice. Okay? This goes pretty cold, right? You can get gaseous carbon dioxide off of a block of dry ice at negative 78 degrees Celsius. Pretty cold. So sublimation is used to prepare freeze-dried foods for long-term storage, right? Because water vapor will change to solid on contact with a cold surface. So you can freeze-dry it, right? Freeze-dried foods have a long shelf life because they contain no water at all. So it just makes it so they don't break down so fast. All right, so a couple more different changes of state are evaporation, boiling, and condensation. I think you know what boiling is, right? Boiling is a liquid to a gas, right? This is also a liquid to a gas. Evaporation, liquid to a gas, which I've said in class. I really don't want to do much with that term there, but the book uses it, so we'll include it here. And condensation is a gas to a liquid. Okay, so water evaporates when molecules on the surface gain sufficient energy to form a gas, right? We're mostly interested in boiling when it does it at the temperature, at the boiling point, right? And then condensation is when gas molecules lose energy and they form a liquid, okay? So I don't want to say anything about that. All right, so let's move on. Now, when water is boiling, all the water molecules acquire enough energy to form gas. All of them do, and that's why I'm really more interested in this, okay? Bubbles of vapor appear throughout the liquid, and you've seen it. You get a rolling boil, and you'll see bubbles coming out because the molecules of the liquid are converted to gas throughout the liquid as well as at its surface. All right, so heat of vaporization is just like we had for heat of fusion. That's the heat that it requires to go from a liquid to a gas, and it's the same heat that it requires to go the other way. It's just negative, right? If it condenses, it's going the other way. It's absorbed. The water absorbs it when it's boiling, and it releases it when it's condensing. Okay? So heat of vaporization for water is 540 calories per gram, right? Going from a liquid to a gas, it's going to require 5 plus 540, right? Or if you're going from a gas to a liquid, you're going to get 540 calories per gram out of it, right? And so here are some conversion factors that we might want to use, right? We've been setting these up for some time now. There's some conversion factors, and let's do a learning check, and then we'll move on, okay? So pause the video here and set this up, and then I'll do it, and then check your work against mine. Okay, so let me suppose that you did pause the video, and its equation is going to be the same as the other one, except this time we're going to say heat of vaporization, right? We just get the amount of heat is going to come by the mass times the heat of vaporization, because the way it's defined, right? So we have, in this case, 50 grams, 50.0 grams of steam from a volcano condenses at 100 degrees Celsius, right? And the heat of vaporization, or the heat of condensation, is 540 calories per gram. Were we asking for joules? Kilojoules, sorry, asking for kilojoules. So let's use this other number here, 2260 joules per gram. Whoops, whoa, back over here. 2260 joules per gram, right? Grams cross off, and we're going to get, asking for kilojoules, so we'll convert that last. 50 times 2260 equals 113,000. 113,000. 113,000, right? Joules. And watch this. This was 3 sig figs. And this was 3 sig figs, right? So this will also be 3 sig figs, and we'll say we're going to report this as 113 kilojoules, and there's our answer. All right. In our next video, we're going to put some of these concepts together now. This is getting more complicated, so hopefully this made sense. If not, go back and watch this one again, because we need these as building blocks for the next videos.